So welcome to this today's class. More than some 22 people are there. So in the last class, we were discussing about search for the mechanism. Search for the mechanism. Uh, we discussed one problem. That problem. Uh, that problem is this. We need to find out the rate for this particular reaction. 2A plus B gives A to B. And they gave the rate also. This is the rate which should be given, come from this non-elementary reactions. So he is asking you to devise a mechanism. He is asking you to devise a mechanism so that we get this rate, right? So for this, he will give you intermediates can be formed. How you are going to form the intermediates, everything that's up to you, right? So sometimes he will ask you to give the what do you call assumptions or something like that. Sometimes he'll give you chain reaction does not occur. If he didn't give you chain reaction does not occur, then what we have to do, you have to go for a chain reaction where there will be 3 steps. Since in the problem itself he is giving you chain reaction does not occur, only 2 steps you are making. So this is how I'm making. 2A gives A to star and A to star plus B gives A to B. So we are dividing this non-elementary reaction into series of elementary reactions. There are 4 now. So then what we do is we will write the overall rate of formation. That is what is asked in the problem. Then if you write the overall rate, what will happen is this A2 star, it will come in terms of A2 star, which is unmeasurable quantity because we don't know whether A2 star is formed or some other thing is formed. So you have to eliminate it. We can eliminate by writing again formation and disappearance. Then finally, you get A2 star in terms of measurables. Then substitute that in the main expression. That is what we did in the last class. So we wrote the rate of formation, rate of disappearance. So he is asking you net rate of appearance or net rate of formation. So formation minus disappearance. So you are getting A2 star, which is unmeasurable. Then we have to write A2 star in terms of measurables. That is what we'll do in terms of rate of formation and rate of disappearance of A2 star. So we equate one assumption that at equilibrium, how much rate of intermediate is formed, that much rate of intermediate is disappeared. So that is what you will put here. So if you put that, then A2 star you are getting in terms of measurables. This all we know, K1, K4, K2, K3. This we have to substitute in the main equation. Then if you substitute and then take the LCM and do some assumptions, then what will happen? You get the final form. But if you see the final form, you are getting everything is correct except 2A. That is what is giving, but we got 2B. That means that what we assumed the formation of intermediate is wrong. So you have to go for another mechanism. That mechanism is this: A plus B is giving you AB star and AB star plus A, because 2A is giving you product. It will give you A to B. Again, if you do, we will get in terms of AB star. Then AB star, if you write what do you call formation and disappearance, then back substitute, you get the final form. That is what we will see today. Rate of formation of A to B. A to B is formed in third step, and disappeared A to B is in the fourth step. You can see here. Here one important thing is formation is not only A to B is here. Disappearance is K3. Net rate is nothing but formation minus disappearance. So formation is 3 and disappearance is 4. Right? So if you, as you see, you are getting in terms of unmeasurable quantity AB star, then you have to write AB star in terms of measurables. So net rate of formation of AB star is formed in K1 and K4. So that is what K1 and K4. Like the disappearance is K2 and K3, K2 AB star and K3 AB star into A star, right? So that is what we put. Now at equilibrium, these two are same. So if you equate formation and disappearance, this is what we get. From this, we can get AB star because it is a common. If you take AB star, then you are getting this. Now this substitute in this equation. Substitute in the net rate equation here and then take the cross multiply and LCM. This is what K3 into this KB star minus K4. So you take LCM K2, K3, multiply this and then take the LCM. That is what we did here. So if you multiply K3A into K1AB, this A into multiplies together to give you square. K3A into K4 A2B into A. Now if you multiply here K4 K2 A2B, K4 K3 A into A2B. So this plus and this minus both gets cancelled out. You get two terms in the numerator and two terms in the denominator. If you see our expression, we are getting this as something and this term is not there. So we can eliminate this term by putting K4 is negligible. That is the rate of disappearance of A to B is negligible to that of formation. Because why we are making that assumption? Because we are writing the net rate of formation of A to B, not the net rate of disappearance of A to B. So we can assume that K4 is much lesser than K3. Therefore, this term will be going to 0. So you are left with this particular equation. So in that, he is asking you here 1. Therefore, divide the entire numerator and denominator by K2. Then what will happen? This becomes 1. This term becomes 1. Here it becomes K3 by K2. And here it becomes K3, K1 by K2. So now you make one more assumption that K3, K2, K1 divided by K2 is around 0.72 because these are all constants. You can measure whatever you want. Then if you are making this as constant, then it becomes 0.72 concentration A square, concentration B divided by 1 plus this is 2 is giving you. Now you assume that K3 by K2 is 2, then 2A. This is the expression which you are required. That is what I am doing here. I am dividing by K2, then you are getting 1 K3 by K2. So this you make it as 0.72. That is what he is giving in the expression. And this you make it as 2. Then if you back substitute, this is the you are getting. RAB is, and you are substituting K4 is less than K3 because we are writing the net rate of formation, not the net rate of disappearance. So you are getting this final form. This is the final form which is required. So since the observed rate is obtained is equal to whatever is the given rate, so we can write our mechanism is correct. This is how you have to search the mechanism or search the rate expression for non-elementary reactions. Any doubt here? Shall I go for one more problem so that we get comfortable? Yeah, please, one of you answer that.
Yes, sir.
Yes, sir.
So you have to write the overall rate, either it is disappearance of appearance. Then what you have to do? The overall rate, it will come in terms of some intermediates. Then you have to eliminate the intermediates by writing rate of formation and disappearance. That's all. Okay. So 52 are there. Good. What is his name? Rajshekara. Who is the class? Guru Murthy. Guru Prakash. You can take the attendance now. 52 are there. 52 are there. So 53 now, I think. So rest of the people will be absent. So take attendance. Okay. Shall we do one more problem now? Yeah. Anyhow, this notes I put already in your LMS. You can download this notes. So if you want to be with me, it is better always to write your running notes so that whatever I talk, it will be, you can, it makes some sense. Otherwise, I'll be in some world and you will be in some other world, right? So it's always better to write a running notes, but the same notes, whatever, this is my class notes actually for your some 2 years, I think 3 years senior, this notes. So she wrote neat notes. So I just asked her to send a what do you call scanned copy of it. This scanned copy of the student notebook, right? Which I took it. Okay. So experiment shows that a homogeneous decomposition of ozone. So he's giving you decomposition of ozone. That means that you have to write net rate of disappearance, right? So minus RO3 is KO2 square, sorry, O3 square and O2 power minus 1. So this is the rate is giving you. So what is the question is asking you? What is the overall rate of the equation? State how you will proceed with the test with the mechanism. So he gave you rate and is asking you to write the mechanism. So he's giving you decomposition of ozone. So what we do now? I think this is some other thing. This is some other. I think ozone we will do now. Because at the time I gave some what do you call assignment for them. I think ozone they might have written. See, yeah, ozone. So we know that decomposition of ozone is O3 gives you O2, and if you balance it, 2O3 gives 3O2. This is the equation which we have to consider, and he is writing the rate of decomposition of ozone. He gave already. So what mechanism we'll choose is, yeah, this mechanism is random. Sometimes it will be correct, sometimes it will be wrong. It's not that only like this you have to split. You can split whatever way you want. And as long as you get the final form, what is giving you in the question, it is correct. If the final form you're not getting, if the final form what you get and what is given in the question is wrong, then you have to go tell that your assumed mechanism is wrong and you have to go for the one more set of mechanism, just like the previous problem. So what I assumed is here O3 is giving you O plus O2. O is nothing but an intermediate. You can put star. That girl didn't put a star. So that intermediate again it is reacting with O3 to give you 2O2. So if you add all the reactants and all the products, then what will happen? 2O3 plus O gives O plus 3O2. So O gets cancelled out. That is intermediate. So 2O3 gives 3O2. That is correct, right? So this should be balanced. Whatever way you are splitting it, the final should be balanced. That is, you have to add all this, and then if you add left hand side and right hand side should be equal to this particular thing, right? Now again, now we write rate of decomposition. So net rate of decomposition is nothing but decomposition is asking you. So formation, yeah, that is what overall rate is minus RO3. Minus RO3 is nothing but where it is formed and where it is removed. So where it is formed, O3. So K1 is because we are writing for a negative first. So net rate of disappearance is nothing but disappearance minus appearance. If we are asking appearance minus disappearance, because we want a positive quantity. So K1 O3 is the disappearance, right? So appearance again it is K3 O because this is also a disappearance. This is also a disappearance, and appearance is K2. Appearance is K2, and if you equate both, yeah, that is what he is giving you. K1 O3, K1 O3. That is what K1 O3 is. K2 because here it is disappeared, and here it is here it is disappeared, here it is formed, and here it is again disappeared. So disappeared is 2 and formed is 1, right? So here I am not putting again fourth equation because I can put that K3 is less than K4 is less than equal to K4 K3. You can put if you want, right? It's not that how you split it, that depends on you. You can put a single reaction or even a reversible reaction. So I am putting only 3 reactions here, 2 for disappearance and 1 for appearance. So if you equate, then I get where is that? This is the overall rate. So then you are getting in terms of O. That O we have to eliminate it, O or O star. That is nothing but again write the formation and disappearance. Then what will happen? O will have K1 O3 divided by K2 O2 plus K3 O3. So here K1, K2, K3, everything you know, O3 and O2 concentrations we can find out. So this, if you substitute, back substitute in R minus RO3, and then you do some cross multiplications, two things will get cancelled out. Generally, two things will get cancelled out because you are writing the rate of appearance and disappearance. So definitely it becomes cancelled out. If you are not getting cancelled out, that is one negative and one positive, that means that you did somewhere wrong. So if you cancel out, then you are getting K2, K2, K1, O3, O2 divided by K2, O2 plus K3, O3. Then again, you make some gimmicks here. Actually, this is not coming, am I right? Because what he is asking you is the mechanism you are not getting that mechanism. That mechanism, that final form is different. This is the final form. Yeah, this is the final form. K O3 square divided by O2. That is what it should come, or O2 power minus 1. So the formed mechanism is wrong, what she did. Therefore, they will go for one more mechanism. You can go for mechanism 2. That is O3 is giving you O2 plus O, and O plus O3 gives 2O2. Again, they do the same. I think she did wrong there. Now, if you again write O is like this, then if you back substitute, then do some what do you call LCM and all, then you are getting like this. So here you make some assumptions that K3 is nothing but the disappearance of O is much lesser than the appearance or disappearance or appearance. Then what will happen? This will be 0. Then you are left with 2K1 K3 by K2. That you make some value. Then you are getting K3 square by K2. That's what. K3, 2K1 K3 by K2 is let it be some capital K. These are all constants. So you are getting the final form. This is how you have to do if it is non-chain mechanism. There are some things where you have to go for a chain mechanism. I'll show that now. This is the chain mechanism problem. I'll show the problem first. I think I'll show the problem first. I'll show the problem. Where is the problem? I think she didn't write. I'll just give me 1 second. Yeah, this is the problem which we did now. Minus RO2 is K whole square. He is asking you overall order of a reaction. That is nothing but 2 minus 1. That is 1. 1 is the it is getting cut, I think. Is it audible, ma? Am I audible?
Yes, sir.
Yes, sir.
Guru, I think 60 people are there. You can give the rest of the attendance. So this is the problem which I liked a lot of times he gave in the exam. This is the problem. Show that the following scheme, N2O5, that is the disappearance is giving you. N2O5 is NO2 plus NO3 star, and NO3 star is giving you NO star and O2. NO star, that is star is nothing but the intermediate. This intermediate plus this intermediate is giving you 2NO2. So here in this problem, what is giving you is giving you that he is giving you the mechanism. Is giving you the mechanism. Is asking you, you find out the rate. That is what is proposed by this fellow in this journal in 1947. Is consistent with and can explain the absurd first order decomposition of N2O5. So this is the problem. He is giving you here the scheme, that is the mechanism. He is asking you to calculate the order. The order should be first order. That is disappearance is what? Minus R N2O5 is something constant into N2O5. That is what? Concentration of N2O5. That is the first order. So how we can get? This is a chain mechanism, you know, because intermediates are formed. That intermediate is giving you one more intermediate. So initiation, propagation, and termination. So how can we do now? You have to write the overall rate of disappearance of N2O5. When you write the overall rate, what will happen is you are get in terms of one intermediate. So you have to eliminate that intermediate. So write again the appearance and disappearance of this intermediate. Then what will happen when you write the appearance and disappearance of intermediate? What will happen is you get this NO3 in terms of NO star. So intermediate when you are doing, again it will come in terms of one more intermediate because of the scheme. So again you have to do appearance and disappearance of NO. Then you get one constant that you have to substitute in this NO3. Once you substitute in NO3, NO3 will come as a constant that you back substitute here. Then you will get the final form. You understood what I mean to tell? So when there is a chain mechanism, when there are some two intermediates which are being formed, the main reaction consists of one intermediate. And if you want to eliminate that intermediate, if you write the appearance and disappearance, it will come in terms of one more intermediate. So you have to eliminate that intermediate also. Then if you write the appearance and disappearance of second intermediate, then you will get a constant. That constant you substitute in first intermediate, then you get a constant value for NO3 star, or NO3 star will be in terms of measurables that you can back substitute here to give you the final rate. So 2 times you have to do. For 2 intermediates, you have to write appearance and disappearance. Now we'll see that by using this. This is the thing what one second, give me, I think I missed somewhere. Yeah, meanwhile you can start writing. If you can write, you write. This is the just now I went. Yeah, this is the problem, right? N2O5 is giving you K1 formation, that is disappearance and formation. Again this and again this. So he's asking you net rate of disappearance. So we'll write the net rate of disappearance. She is writing. Yeah, this is the net rate of disappearance. Net rate of disappearance is nothing but K1 N2O5 is equal to or minus or whatever you call NO3 K2 NO2 plus K3, all that. Yeah, you can see net rate of disappearance is minus R N2O5 is K1. K1 first step it is disappearing. Then K2 is appearing. So one minus the other, you are getting in terms of NO3 star, which is unmeasurable quantity. So we have to write NO3 in terms of measurables. This is the first step. Net rate of disappearance is disappearance minus the appearance. If you are writing net rate of appearance, then it will be appearance minus disappearance. So how you are writing that comes first, because you need a positive quantity. So minus R N2O5 is K1 is step, and this is the reverse step. So reverse step is having what do you call intermediate. So you have to eliminate this intermediate. That intermediate can be eliminated by writing appearance and disappearance of yeah, rate of formation of NO3, where NO3 is formed, K1 step, and where disappeared, it will be in 2 steps, in fact 3 steps it will be. K2 step it is there, K3 step it is there, K4 step. So if you equate these two, then NO3, NO3, NO3 you will get. So if you take a common, and then if you equate K1 N2O5 divided by K2 NO2 plus K3 plus K4 NO star, it will come. So NO3 star is having one more unmeasurable quantity, K NO star, right? So that is what you will be writing here. Yeah, that is what. So NO star, if you write, rate of formation of NO is K3 step, disappearance is K4 step. Then if you equate these two, that is what K3 NO3, this. So NO star is what we want. NO3 gets cancelled out. Therefore, NO is K3 by K4. It's a constant now. This you substitute in K3. Now substitute back in this particular thing, and then take NO3 star. NO3 you are getting like this. This is in terms of measurables now. There is no NO star. Now NO3 you know, which is measurable. That you substitute back in this equation. Substitute this plug in here, and then take some LCM and make some cancel out. The two terms will be cancel out, and then rest of the term is 2K1 K3 divided by this. So make K3 as divide. Yeah, this is what you are getting. So divide by K3. Then what will happen? K3 gives 2K1 is here. 2K3 you divide. K1 N2O5 divided by 1 plus K2 by 2K3 N2. What is asked? He is asking here in terms of first order kinetics. Am I right? He is asking it should be observed as the first order decomposition of N2O5. That means that you have to get K into N2O5. That is what we got here, K into N2O5. But this is the denominator part is there, 1 plus something. So if you can make this particular thing as very small, then you will get that is what we'll assume. K2 by 2K3 NO3 is very small. That is K3 is very small compared or very greater compared to K2. K3 is very greater compared to K2. Then what will happen? This fraction becomes very small. 1 plus very small is almost 1. Therefore, you get N2O5, K1. That is nothing but the first order decomposition of N2O5. That means that whatever is observed mechanism what he gave, it is consistent with this particular thing. All right. So observed mechanism what he gave is correct. So this is how you have to do for chain mechanism. 2 times you have to draw. Any doubt here? Any doubt, man?
No,
I'll give
sir.
you some more problems. You can see some more problem like here you can go. I think this is the book, Levenspiel book. This is the exercise problems. So you can do one more problem here like this. I think, yeah, you can show this also. See, show that a following scheme mechanism of azomethane decomposition is like this. A plus A gives A star plus A. That A star is decomposition to give you R plus S is consistent with the observed kinetics. Right? Different mechanism can be proposed to explain the first order kinetics. To claim this, a mechanism is correct in the face of other alternatives required for additional information. So you take this and then see it is first order kinetics, right? That is one. This is a problem we did. You can use one more problem like this. This is what we previously we did it. Come up with or guess a mechanism that is consistent with experimentally found rate equation. So he is giving you K A to B, 2A plus B gives A to B. So try to get this particular equation, right? That is one. There are a lot of problems like that. I think before they gave one more problem, H2O. Yeah, you can try this. This is also a very good thing. The decomposition of nitrous oxide is found to proceed in the following. N2O gives N2 plus half O2. So decomposition is giving K1 N2O square divided by 1 plus K2 N2O. So he's asking what is the order of this reaction with respect to N2O, and he's asking you what is the overall order. So he is giving you the rate. That means that you have to find out the mechanism. You have to find out the mechanism, right? So that is what I think this girl did. I'll just run through that. I'll just give you the. Yeah, this you can see here. N2O gives N2 plus half O2. This is the observed mechanism is giving you rate. You can do whatever mechanism you want. This girl did with N2O plus N2O because she is trying to get N2O down also is there. Therefore, N2O plus N2O, that is 2NO2, gives equilibrium N2O star N2O. This N2O is giving you N2 plus half O2. N2 plus half O2. That is what how she is making. But if you make like that, then what will happen? N2O is 2NO2. Then it is not getting balanced. The here itself you can see. So this goes wrong. So when you are splitting it, see to that again it is going to correct. Yeah, it is correct because N2O, this here also you are getting N2O, that gets cancelled out. Yeah, it is correct now. It is balanced because 2NO2, NO2 star, NO2 star get cancelled out. 2NO2 star is N2 plus half O2 plus NO2. So NO2 get cancelled out. Correct, right. So you can write the appearance and disappearance. It comes in terms of NO2 star. Then you write again the appearance and disappearance, and then you get it. That is what she did here. Formation of N2O, because he is asking for the disappearance here. So he is writing for the formation, the disappearance. So net rate of disappearance is nothing but disappearance minus the formation. So that is what she did here. So you are getting in terms of N2O star. So again, write formation and disappearance for N2O star. So if you do it, then N2O star you are getting in terms of measurables. That you back substitute here and then do some manipulations, cross multiplying, all that. Then you are landing with this kind of equation. That is what is giving you. So K2 by K3, let it be some K2. Because you can put whatever constants you want. That is what he is giving in the problem. So let you put K2 by K3 is some capital K2. That is what he asked. Am I right? So this is what he asked. Like that, you can do n number of any reaction. You can do with any reaction. That is what I earlier itself told. So this is the problem which they asked one more. For show that the following scheme N2O, N2O5 gives NO2 plus NO3. N2O plus NO2 plus NO3 star gives NO2 plus O2 plus NO. NO plus NO3 gives 2NO3. Is consistent and can explain the first order kinetics. This is what just we did. So you can do some more problems like here also. This is going to be the biggest challenge. So H2 plus Br2 gives 2 HBr, is giving you the rate. The formation for HBr is this. So how you have to write, that is what also is giving you. Initiation, propagation and termination. So you have to write in terms of two, what do you call, intermediates, Br star and H star. That do that, right? So this is what he is giving you. From this, you try to get this particular equation. Any doubt here? Can I go for the next thing?
Yes, sir.
So you have to do, unless you do, it looks as if it is very easy. But actually, if you do, it becomes very complicated because too many equations will come. And you have to rightly substitute in what equation that particular thing. So today we discussed more about this, what do you call, search for the mechanism and all. Now we'll go to the next topic. This is the same type of thing. I'm not going to do this particular thing here. The next one is temperature dependent term of a rate expression. Temperature dependent term of a rate expression. How to find out this temperature? Temperature, we already know that the rate is a function of temperature and composition. But as long as the temperature is constant, we are assuming it is K is constant and F2 is the composition. But this K is called as a rate constant and Ri is called as a rate equation. Don't get confused with K and Ri. Ri is the rate expression. K is the constant, rate constant. So both will have a units. It's not that rate and K will have the same unit. The unit of K, it changes, and Ri also it changes, right, with the rate. According to Arrhenius law, this K can be written as K is K naught into e power minus E by RT. That is, K is pre-exponential factor, an exponential of minus E by RT, where E is the activation energy and R is the gas constant and T. So if you do an experiment, if you want to find out how the rate is going to change, you have to do an experiment with the T. That is, as the time increases or the temperature increases, how much is the rate changing? So if you are having that data, you can plug it this in this equation. How to plug this equation? This is, you take a ln on both sides, then what will happen? Ln K is ln K naught plus e power minus E by RT is nothing but log A into B. That is nothing but log A plus log B. Therefore, ln K is ln K naught. You have to do ln for this. Log of an exponential is this. Therefore, log of an e power A is A. Am I right? So this becomes minus E by R into 1 by T. If you take a log, log of E becomes nullified. Therefore, only left with the power term. That power minus E by R into T. So here what is happening? Ln K. K naught is constant because this is the pre-exponential factor. Minus E by R. E is constant, activation energy. R is constant, 1 by T. So if you can draw a graph between ln K versus 1 by T, this is in the form of y is equal to, this is M, this is X, this is the independent variable X, and this is the what do you call, intercept. This is the intercept. That is what we did here. Ln K versus 1 by T, 1 by T on the y-axis, ln K on the x-axis, because you are getting a negative slope. This minus E by R is nothing but slope of equation, though this is in the form of y is equal to mx plus c, where m is the slope and c is the intercept. So if you want to find out what is the pre-exponential factor, you can find out the intercept. So you can see here, take this equation, take this line. So this is forming here. Therefore, this becomes ln K naught. From that, we can find out K. And if you find out the slope of this equation, it will give you minus E by R. Whereas R, you know, gas constant, then you can find out what is the activation energy for that particular reaction. Any doubt? Any doubt, ma? In this? Now, what will happen if the activation energy is very high? Activation energy is nothing but the energy required for minimum energy required for the reactant to react. So if there is a high activation energy, you can see here, this activation energy is very high. Then what will happen? E by R is the slope. So minus E by R is the slope. Therefore, your slope becomes very steep. That is what your equation, your line becomes very steep. Therefore, your intercept becomes very more. Now, if the activation energy is very less, then minus E by R becomes less value. Therefore, your almost the equation becomes a straight line like this. So for a low activation energy, you get this kind of curves. For a high activation energy, you get this kind of curves. This is not what we want. We want how the rate changes with respect to the time, temperature. So for that, what we need to do is you can put different temperatures, T1 and T2. Yeah, you can put now. Let a temperature T1, let K is K1. At temperature T2, let K is K2, T is T2, and K is K2. So if you substitute here, what will happen? Ln K1 is Ln K0 because this is constant minus E by R into 1 by T1. If you substitute second temperature, then what will happen? Ln K2 is Ln K0 minus E by R into 1 by T2. So you get two equations. One is with the Ln K1 and one with the Ln K2 with the different temperatures. So what we have to do, how this K changes with the different temperatures. What you do is you divide one equation by the other, Ln K1 divided by Ln K2. That is what we did here. Then what will happen? Ln K1, this gets cancelled out. Minus E by R, 1 by T1 minus 1 by T2. That is what you get. Ln R2 by R1 is nothing but the rate at new place divided by the rate at old one is Ln K2 by K1 is E by R 1 by T1 minus 1 by T2. This also you can do here. That is what he is giving you here. Ln K2 by K1 is E by R 1 by T1 minus 1 by T2. So we know what is the temperatures. At T1, your rate is K1. At T2, we don't know the rate. Then you can find out using this equation. You know what is the activation energy required. He'll give you in the problem. If he is not giving you in the problem, he'll give you an experimental data. From experimental data, you can draw a curve between Ln K versus 1 by T. Then find out the slope. Then you can get E. That E you can substitute in here and then calculate. You know what is T1, what is T2, what is K1. Then you can calculate K2. That is how the rate is changing with respect to the temperatures. Any doubt here? Any doubt here?
No, sir.
Can we do a problem now based on that? This equation, right? We'll do some problems now. That is what in here is giving you. Yeah, I'll show you some problems. Let us do some problems here. This is the exercise problem of 11th bill. Now, this is the first question. Yeah, please, number 52. Please read this first question. What I am showing, 2.1. Yeah, 52. You are there? Number 52. Who is 52, man? No? Then 53. Please read the first question. 53.
A reaction has this stoichiometric equation A plus B equal to 2R. What is the order of the reaction?
Yeah, can you tell the order of a reaction? Make a try. Let it go wrong, no problem. Yeah. What
Sir?
will be the order of? Yeah, make a try. What is the order of a reaction? These are all just 2 marks questions.
Yeah, 2 I guess, sir.
2 you guess, good guess. Yeah, any other student can give the correct answer or will agree to him or disagree to him. Number 39, you're there. 39. He's telling A plus B gives 2R. He's telling the order of a reaction is 2. Is it correct or wrong? 39. Number 40. Forty-one. Again, I'm repeating you. If you are not responding, then I have to do some other means, right? You have to respond. You cannot be a silent spectator there. I'm calling this many numbers. Only one number responded. But I am seeing in the thing 60 people are there. Only 5 absentees. Yeah, 42. You're there, 42.
Yes, sir.
Yeah. He told
I think order is 2.
Order is 2. You are also thinking order is 2?
Yes.
Correct? Okay. Can anyone give some other answer other than 2? No one is giving any answer. I tell that order we cannot tell. Is it correct? Will you agree with me? I tell that order we cannot tell.
Yes, sir. Because it's not given, it's an elementary reaction, sir.
Yes. Unless he mentioned it is elementary, we cannot tell the order is 2 just by looking at the expression. This is sometimes, if you go to some interviews, they'll give you an equation. They'll ask you what is the order of this reaction. Yeah, it looks 2, but if it is an elementary, then it is 2, because the rate expression corresponds to CA and CB. Therefore, power is 1, then it is 2. But looking at the equation, we cannot tell the order unless you have to ask immediately whether this equation is reaction is elementary. So those people who is telling 2, it is wrong actually. Though it is correct, but it's not the correct way, right? So now can we tell this equation given the reaction 2 NO2 plus half O2 gives 2 N2O5. What is the relation between the rate of formation disappearance of the 3 components? Yeah, can anyone tell the answer now this for this? So we have to write the rate of disappearance, appearance of both. Yeah, how to do that? Relation. There's nothing but minus R NO2 divided by its stoichiometric coefficient is minus O2 RO2 divided by its stoichiometric coefficient is R N2O5 divided by its stoichiometric coefficient. That is the rate of appearance and disappearance. That is what is that, right? Relationship between both. Now here this is an important question. One important question. A lot of people get confused now. A reaction with a stoichiometric equation, half A plus B gives R plus half S, has the following rate. Right? The rate is minus RA 2 times CA power 0.5 CB. Correct. Now what is the order of now what is doing is what is the rate expression for this reaction if the stoichiometric equation is written as if you multiply this, A plus 2B gives 2R plus S. Then if the multiply this particular thing, what will happen to the rate? Whether it will remain same, whether it will be changed? Yeah. Can anyone tell this question? It's a beautiful question. Anyone? It's open to.
It will remain same.
It will remain same. Very good. Why it will remain same?
Because order is independent of stoichiometric coefficient.
Order is independent of stoichiometric coefficient. Good, good, good. Any other answer? Good. What is your name? Just now. What is your name?
So roll number 46, sir.
What is your name?
Rohit, sir.
Rohit. Good, Rohit. Answer is absolutely correct. Any other answers can give? Since I told it is correct, so no one wants to tell. Why it is correct is, now you see, this equation is an elementary reaction because your corresponding rate is corresponding to the stoichiometric coefficients. Here 0.5 and here it is 1. So for an elementary reaction, that means your rate is corresponding to this. For that, you again multiply with any coefficient or even divide by any coefficient. This is what you multiplied here. The rate expression remains the same for an elementary reaction. Since it is an elementary reaction, here it is same. If it is non-elementary, then it may be changing. We never know, right? That is the answer for it. Good, Rohit. So the problem what I want now is here. Yeah, can anyone do these problems 2.6 and 2.7? You can do that problems 2.6 and 2.7, right? The problem what is here? Yeah, the pyrolysis of ethane proceeds with an activation energy of about 300 kilojoules per mole. So he's giving you activation energy. He's asking you how much faster is the decomposition at 650 degrees centigrade than at 500 degrees centigrade. So he's asking to giving two temperatures T1 and T2 and is giving you E, activation energy. He's asking you how much faster is the decomposition. We know that decomposition, as the temperature increases, the decomposition will be faster, maybe exponential. He's asking you how much times it is the first. So you have to find out K2 by K1. So the expression for that is, we know that, right? This expression, yeah. K2 by K1, that is what we want. So K2 by K1 or Ln is E by R. E is giving, R is given 1 by T1, 1 is 1 by T2. Here when you substitute, the temperature should be in Kelvin because R value is in Kelvin. So that you remember, then only it gets cancelled out. Otherwise the unit remains. Since R value is in Kelvin, gas constant values are in Kelvin. So you shift your temperature from centigrade to Kelvin. That means you add 273 to it. E is known, R is known, 1 by T1. Then you can find out K2 by K1. That is the how you have to do. That I think she did it. We'll see that problem. The same answer. This will be the last thing. Then we can wind off today's. Yeah, this is the problem I asked you to do. You can do that. Where is the problem? Yeah, this is the derivation for it. So K1 by K2, if you do, Kn by K0, it gets cancelled out. You will get that particular expression, right? She didn't do this problem here. Answer. Yeah, this. The pyrolysis of ethane proceeds with an activation energy. How much faster? At 650 and 500. So R value is 1.98 calories. So we know that ln K2 by K1 is E by R, 1 by T1 minus 1 by T2. That is nothing but ln R2 by R1. So E is this, he gave you in calories. Since E value is in calories, R value also is substituted in calories, 1.9. If E is giving you in terms of joules, then you substitute R value in terms of joules, 8.314. So the substitution of the value of R depends on the unit of E. E is giving you in calorie, then you substitute R value in calorie. If E is giving in terms of joules, then R value is also you substitute in terms of joules. Here important is 500, 600 should be converted to Kelvin because R values is in Kelvin. R value is in Kelvin, right? So if you substitute in terms of Kelvin, then you get ln K2 by K1 is this. So we want how much is the faster. K2 by K1 is 2838. So K1 at 500 degrees centigrade, if your rate is K1 at 723, that is 700 degrees centigrade, your rate is shooted up to 2838 times. So from this example, we can tell that the rate is a strong function of temperature. It is exponential. It's not that one time, two times it will increase. even a small change in temperature, your rate shoots up like anything. That is why we need to maintain isothermal conditions in the reaction. Otherwise, the rate will abnormally change. Abnormally change. Right? Yeah, I stop here. I think it is 11:57. Any doubt, ma? Like that, you can do the problems. Like that, you can do. Lot of problems are there. This also you can find out. Well, Kelvin is giving you N known N thermally cracks 20 times as rapidly as this particular thing. So he's giving you two temperatures and then he's giving you K2 by K1 20 times. He's asking you the activation energy. Earlier problem, he gave you activation energy. He's asking one, how much time faster. Here he is giving you how much time faster. He's asking you activation energy. It's the reverse. You can do that also. Right? So like that, you can do all these problems. These problems are all very important, very good problems, very thinking problems are there. So try to do that. Huh? Yeah, I stop here. Yeah, any doubt, ma? I stop here. I think Guru can take the attendance.
Sir, now again I will take the attendance.
No, already 60 people I told you to take. How many absentees are there with you? 5. How you are taking the attendance?
I took the screenshot, sir. Then I will match the
Then
name list and I will tell the absentees.
Yeah, okay, fine. Now I think it is 5 people are absent. Huh?
6, sir.
Yeah, 6. Okay, yeah. If 60 includes me. Okay.
Yes, sir.
Then 6 people will be absent. So try to send the attendance. And already the attendance I'm updating in the LMS. You can check those people who gave some internship or something like that. You please try to send the letters to me. Some 2 girls sent, I think. I'll mark OD. So you can check your attendance in the LMS. Okay. The moment Guru sends to me in the chat, then definitely I'll once I upload, then I'll send a reply to him that it is uploaded. Then you can see. Okay. So I'll stop here. Then continue with the next topic in the next class. Thank you for joining. Any doubt? Yeah, you can put in the chat, WhatsApp chat, or you can call me and find out. So meanwhile, you try to do a lot of problems because CRE is everything about problems only. So you have to do more problems, exercise problems, some example problems. You can see Gawane book. They'll give you a lot of problems, solution to the exercise problems. And then you would start doing it. Once you start doing it only, you'll get a lot of doubts. Then I try to clear your doubts. Okay. Thank you for joining. I stop the recording now. We can meet